Okay, once we discuss on which concepts we have to focus from electrochemistry, okay, some conclusions we will discuss, important conclusions and important equations, right. So in local exams and in JL type of exams, DL type of exams, almost you will get 80% of the questions from this short notes, okay, if you have application knowledge, okay. So after practicing these equations, these important points, okay, next you have to practice as many bits as possible, and once if you practice bits, your application knowledge also developed, okay. So you follow these two and short notes and as many questions as possible you may practice. Almost 80% of the questions will be covered from this short notes itself, okay. Now, okay, electrochemistry, we know electrochemistry deals with what? And electrochemistry deals with conversion of electric energy to chemical energy and chemical energy to electrical energy. So conversion of electrical energy to chemical energy, that we do in electrolytic cells. Electrolytic cells, so such process is called as electrolysis. We do in electrolytic cells, such process is called electrolysis. Chemical energy to electrical energy, okay. The name of such cells are galvanic cells or voltaic cells, okay. Next, what is electrolyte? And electrolyte, the substance which conducts electricity in aqueous state or molten state, that is called electrolyte, okay. Electrolytic conductor, otherwise the substance which allows passage of current through it in its aqueous state or molten state. For example, aqueous NaCl solution or molten NaCl solution. So such substance is called electrolyte. In electrolytes, which particles are responsible for their conductivity? And ions are responsible for their conductivity. Whether there is any material transfer or no material transfer, and material transfer is observed. Chemical changes can take place or no chemical changes, and chemical changes occur, okay. At anode oxidation, at cathode reduction reactions occurs. If you take electronic conductors or metallic conductors, in that which particles are responsible their conduction? Electrons are responsible. Is there any chemical changes or no chemical changes? No chemical changes, okay. So next one, electrode potential. And electrode potential indicated with E. What is unit? And volts. Electrode potential indicated with E, unit volts. What is electrode potential? Tendency to lose electrons or gain electrons. Tendency to lose electrons or gain electrons is called electrode potential. Tendency to lose electrons is called oxidation potential or reduction potential? Oxidation potential. Tendency to gain electrons is called reduction potential. And the relation between these two is oxidation potential is equal to minus of reduction potential, okay. Tendency to lose electrons is called oxidation potentials, tendency to gain electrons reduction potential, just the sign is different, okay. The tendency to lose electrons is also called as, another name I have given, solution pressure, osmotic pressure. Osmotic pressure, okay. Tendency to lose electrons is also called osmotic pressure, OP, and the tendency to gain electrons is called as solution pressure. Tendency to lose electrons is called oxidation potential or osmotic pressure, okay. Tendency to gain electrons is called reduction potential or solution pressure, okay. And electrode potential depends on what? It depends on temperature, nature of electrode and concentration of ions present in the solution. Electrode potential depends on temperature, nature of electrode and concentration of ions present in the solution. Temperature, nature of electrode and concentration of ions present in the solution. Whether electrode potential is extensive property or intensive property? Intensive property. It is independent of amount of substance. It is independent of amount of substance. Standard electrode potential E naught. If you measure under some conditions, that is called standard electrode potential. What are those conditions? Temperature we have to take 25 degrees centigrade or 298 Kelvin, and concentration of ions present in the solution unity or 1 molar. Then electrode potential measured is called standard electrode potential. So we are fixing temperature and concentration. So therefore standard electrode potential depends on what? E naught depends on what? Nature of electrode. E naught depends on what? Nature of electrode. It is a characteristic value of a given electrode. No two electrodes have same E naught value. That's why E naught value we can use in qualitative analysis, and in polarography qualitative analysis is done by E naught value only. In polarography qualitative analysis is done by E naught values only. Okay, next one, is it possible to determine single electrode potential, or it is not possible to determine single electrode potential? Not possible to determine single electrode potential experimentally. We can calculate only difference between two electrode potentials. Difference between two electrode potentials we can calculate by using potentiometer, that is called as cell potential or cell EMF. Difference between two electrode potentials we can determine experimentally. This we can calculate experimentally. What is the formula? Cathode reduction potential minus anode reduction potential. If oxidation potentials are given, to get reduction potentials, what we have to do? We have to change sign. We have to change sign. Under standard conditions, E0 cell is equal to what? E0 cathode minus E0 anode. Under standard conditions. So by using potentiometer we can calculate cell potential. So if you want to determine single electrode potential, okay, when it is possible, and if you combine that electrode with another electrode whose potential is known. Okay, if one of the electrode potentials is known, other electrode potential we can calculate, since E cell we can get experimentally. If one of the electrode potentials is known, another electrode potential we can calculate. So the electrode whose potential is known, that is called as reference electrode. The electrode whose potential is known, the electrode whose potential is known is called reference electrode. The electrode whose potential is known is called reference electrode. We have two reference electrodes. One is standard hydrogen electrode, which is also called as primary reference electrode. Standard hydrogen electrode, primary reference electrode. What about its electrode potential? And 0. Its electrode potential is 0. It consists of inert electrode platinum for electrical contact. Hydrogen gas is bubbled at 1 atmosphere pressure. Hydrogen gas is bubbled at 1 atmosphere pressure on the surface of platinum, which is in contact with what? 1m HCl solution. That is in contact with 1m HCl solution. Hydrogen gas is bubbled on the surface of platinum at 1 atmosphere pressure, which is in contact with 1m HCl solution, whose potential is taken as 0 for reference purpose. Okay. What are the electrode reactions? And if it acts as anode, this is the electrode reaction. If it acts as cathode, reverse reaction occurs. This is the oxidation reaction of hydrogen electrode. It is an example for which type of electrode? Gas electrode. Hydrogen gas is bubbled on the surface of platinum. So this is called as gas electrode. Some other examples for gas electrodes are chlorine gas electrode, bromine gas electrode, oxygen gas electrodes. So all those are examples for what? Gas electrodes. Those gases are bubbled on the surface of platinum. Okay. Next, another reference electrode is what? Saturated calomel electrode, that is also called as secondary reference electrode, since its potential is calculated again by using standard hydrogen electrode. So that is called secondary reference electrode. If you take saturated KCl, what about its potential, reduction potential? 0.242 volts. 0.242 volts. It consists of, what are the various components present? Platinum for electrical contact, mercurous chloride, mercurous chloride is also called calamine. Okay. Mercurous chloride, which is in contact with what? Saturated KCl. Which is in contact with saturated KCl. It is an example for which electrode? Metal insoluble salt. Metal insoluble salt electrode. Okay, for metal insoluble salt electrodes, their electrode potential depends on what? Their electrode potential depends on what? Anion concentration, Cl minus ion concentration. Mercurous chloride is reverse to what? Cl minus ions. So their electrode potential depends on what? Anion concentration. This is an example for metal insoluble salt electrode. For these electrodes, electrode potential depends on what? Electrode potential depends on anion concentration. If you take saturated calamine electrode as reference electrode, if it acts as anode, what is the reduction reaction? Oxidation reaction. 2 Hg plus 2 Cl minus gives rise to Hg2Cl2 plus 2 electrons. This is the oxidation of reaction of calamine electrode. 2 Hg plus 2 Cl minus gives rise to Hg2Cl2 plus 2 electrons. So electrode potential depends on whose concentration? Cl minus ion concentration. Okay. And cathode reverse reaction. Similarly, silver chloride also example for what? Silver chloride is also an example for what? Metal insoluble salt electrode. So generally metal insoluble salt electrodes also we can use as reference electrodes. So if you take silver chloride at anode, what is the reaction? Same, and metal we have to take Ag plus Cl minus gives rise to AgCl plus electron. So here also electrode potential depends on Cl minus ion concentration. If you take AgBr, silver bromide, Ag plus Br minus gives rise to AgBr plus electron. Okay, and so on. Okay. And some other electrodes we have, totally we have 5 types of electrodes. One is gas electrode, next one metal insoluble salt electrode, next one metal ion electrode, metal ion electrode, that is Mn plus only, Mn plus, Ag plus, for example Zn2 plus, copper 2 plus, all those comes under metal ion electrodes. This is third type only. Fourth type, metal amalgam electrodes, metal amalgam electrodes, metal we take in the form of amalgam, that is in contact with its ions. Same electrode reactions are same in both the cases. M gives rise to Mn plus plus n electrons. Here also M gives rise to Mn plus plus n electrons. Electrode reactions are same, only the difference is metal we take in the form of amalgam to decrease its activity. So active metals, alkali metals which are active, which may participate in the reaction with water, such active metals or alkali metals we take in the form of their amalgams to decrease their activity. Okay. So electrode reactions are same in both the cases. Here M gives rise to Mn plus plus n electrons, here also M gives rise to Mn plus plus n electrons. And last type is redox electrode. Redox electrode. So redox electrode means it contains both oxidized and reduced form of same ionic species. If both oxidized and reduced form of same ionic species present in the solution, that is called redox electrode. For example, Fe plus 2, Fe plus 3 both are present in the solution, and platinum for electrical contact. This is an example for redox electrode. For example, both cerium plus 3, cerium plus 4 present, and platinum we are using for electrical contact. So that is an example for redox electrode. Another one is twin hydron electrode. Quinhydron electrode contains both quinone and hydroquinone. This is the oxidized form, QH2 is the reduced form, and both oxidized and reduced forms are present. That's why quinhydron electrode is also an example for redox electrode. This is the reduction reaction. Q plus 2H plus 2 electrons gives rise to QH2. So this is the oxidized form of quinhydron electrode. What is the reduced form of quinhydron electrode? QH2. Q means quinone, QH2 means hydroquinone. Okay. So both are present, and both are present. That's why that is also an example for redox electrode. So these are the various types of electrodes we have. Okay. Next one, cell representation, and how to represent a cell. The general representation is anode and then salt bridge followed by cathode. And while we are writing anode representation, metal followed by metal ion or metal ion followed by metal ion? Metal followed by metal ion. If their concentrations are known, we have to write in the bracket, and we may mention aqueous also, aqueous comma 1m. This is solid, aqueous comma 1m. Next here cathode, Mn plus aqueous comma 1m m. Okay. Anode is represented with negative sign or positive sign, and negative sign. Cathode is represented with a positive sign. Okay, here flow of electrons is observed from anode to cathode. So anode repels electrons, so that indicated with a negative sign. Cathode attracts electrons, that is indicated with a positive sign. If salt bridge is known, that we have to represent in between two vertical lines. For example, we are using KCl salt bridge, that we may represent in between two vertical lines. Salt bridge is known, we have to represent in between vertical lines. So this is the general representation of a cell. For example, if you take Daniell cell, and how to represent Daniell cell? Daniell cell is constructed by zinc and copper electrodes. Okay, under standard conditions, whose standard reduction potential is more? Copper standard reduction potential is more compared to zinc. Copper is 0.34 volts, zinc is minus 0.76 volts. So which undergoes reduction? Copper undergoes reduction, zinc undergoes oxidation. So copper undergoes reduction, so it acts as cathode. Zinc undergoes oxidation, that means it acts as anode. So if you combine two electrodes, which electrode acts as anode, which electrode acts as cathode, that we decide based on their reduction potentials. The electrode whose reduction potential is high, that acts as cathode, and whose reduction potential is small, that acts as anode. So Daniell cell potential and E0 cell under standard conditions, how much? 0.34 minus into minus plus 0.76, that is 1.1 volts. How to calculate change in Gibbs free energy? Minus NF E0 cell. Number of moles of electrons involved for Daniell cell. Zinc in contact with zinc sulfate, copper in contact with copper sulfate. Cell representation is like this: Zn zinc sulfate 1 molar, copper sulfate aqueous comma 1 molar, you may write aqueous comma 1 molar, copper solid, aqueous comma 1 molar, aqueous comma 1 molar, copper solid. So how many moles of electrons are involved? 2 moles of electrons are involved. So therefore we get minus 2 into 1 Faraday is equal to how many coulombs? 96,500 coulombs into 1.1 volt. 1 volt coulomb is equal to 1 joule. 1 volt coulomb is equal to 1 joule. So we get result in joule. So they are asking to calculate delta G naught also only sometimes. Okay. So that is the cell representation. Okay. Next we discussed, I think, transport numbers, then transport into transport numbers. What is the transport number? And that is the fraction of current carried by an ion in the total current. In the total current flowing through the solution, how much current carried by an ion, that is called its transport number. So transport number of cation is given by, okay, its mobility, and that is mobility of cation by mobility of cation plus anions. Transport number of anion is given by mobility of anion by mobility of cation plus anion. Always sum of the transport numbers of cation and anion must be equal to 1. It is also represented as T plus T minus. Sum of the transport numbers of cation and anion is equal to 1. Okay. So the fraction of current carried by an ion depends on what its mobility, and out of all cations whose mobility is high, H plus ion mobility is high. Out of all cations, H plus transport number is high. Out of all anions whose transport number is high, and OH minus ions transport number is high. Okay. Out of all cations, transport number of H plus is high. Out of all anions, transport number of OH minus ions is high. Their conductivity values are also high. Their conductivity values are also high. Next, we discussed concept of mean ionic activity and mean ionic activity coefficient. Generally, activity and activity coefficient we follow for non-electrolyte solutions to explain deviation from ideal behavior. Activity coefficient we follow to explain what? Deviation from ideal behavior for non-electrolyte solutions. But for electrolyte solutions, what we follow? Mean ionic activity and mean ionic activity coefficient. So the formula, generally if you take an electrolyte like this, and MxAy undergoes decomposition to give X moles of cations, Y moles of anions. So stoichiometric numbers of cations and anions are what? X comma Y. Number of moles of cations and anions obtained are X comma Y. Then A plus or minus is given as, what is the formula? A plus power X, A minus power Y, whole power 1 by X plus Y. That is the formula for mean ionic activity. Next, gamma plus or minus also same. Okay, gamma plus power X, gamma minus power Y, whole power 1 by X plus Y. Otherwise we can write like this only. A plus or minus whole power X plus Y is equal to A plus power X, A minus power Y. If you bring this to left side, 1 by X plus Y becomes X plus Y. Same in the with respect to mean ionic activity coefficient also. For example, if you take sodium phosphate and sodium phosphate Na3PO4, Na3PO4, X value we have to substitute 3, Y value we have to substitute 1. Sodium phosphate, calcium phosphate, Ca3PO4 taken twice, Ca3PO4 taken twice, X value 3, Y value 2. Okay. Next we discussed mean ionic molality also. Same and M plus power X, M minus power Y, whole power 1 by X plus Y. This is the concentration of cations and this is the concentration of anions. One question also discussed given in political lecturers exam based on this. So this is the concept of mean ionic activity coefficient. If you see the relation between activity and mean ionic activity coefficient, A is given as A plus power X, A minus power Y only. That is given as A plus or minus whole power X plus Y. Okay, A plus power X, A minus power Y, whole power, that may be written as A plus or minus whole power X plus Y. This is the activity of electrolyte and this is the activity of cation into activity of anion. Activity of electrolyte we can write as activity of cation into activity of anion. Okay. So if you take for 1:1 electrolytes and for 1:1 electrolyte, okay, for HCl 1:1 electrolyte, almost we discussed 1:1 electrolytes only. Zinc sulfate, copper sulfate, HCl, all these are what? 1:1 electrolyte. Number of cations obtained 1, number of anions obtained also 1. X values, Y values 1. And so A activity we can write as A plus or minus power 2. Activity we can write as what? A plus or minus power 2 per 1:1 electrolyte. All the examples we discussed are 1:1 electrolytes only. KCl we discussed, HCl, zinc sulfate, copper sulfate. These are the examples we discussed. Okay, in all these cases the number of cations and anions obtained are only 1. So A is equal to what? A plus into A minus, that may be written as A plus or minus power 2. And in the place of X we have to substitute 1, in the place of Y also we have to substitute 1. Okay. Next we discussed various types of galvanic cells. 5 types we have. The first one, chemical cell without transference. Chemical cell without transference. If we use salt bridge, if we use salt bridge, whether it is with transference or without transference, without transference. If we are not using salt bridge, then two possibilities. It may be with transference or it may be without transference. When we get without transference, and if it is common electrolyte, in such case we get without transference. If you have common electrolyte, even though we are not using salt bridge, that comes under without transference only. So the example we discussed, okay, note direct transfer of ions and from one half cell to another half cell, that is called without transference. Daniell cell with salt bridge or without salt bridge? With salt bridge. Daniell cell with salt bridge. So, before that we have to discuss once Nernst equation also. Okay. Right. After Nernst equation I will explain that. Okay. Right. What is Nernst equation? This is the equation we have. Delta G is equal to delta G naught plus RT ln Q, where Q is called reaction quotient. So in that, if you apply bridge equation between thermodynamics and electrochemistry, delta G is equal to minus NFE, we get expression for E as E0 minus RT by NF ln Q. E is equal to E0 minus RT by NF ln Q. Or if you write at 25 degrees centigrade, what we get? And this value 0.059 by N log Q. N means number of moles of electrons involved at electrode reaction. Q, how to write Q? And product side ions concentration by reactant side ions concentration. If gases are there, we have to write their pressure. If gases are there, we have to write their pressure. How to calculate reduction potential for metal ion electrode? E0 plus 0.059 by N log concentration of metal. Otherwise, just by one step we will get. No need to remember. E is equal to E naught. Instead of writing minus, I am writing plus 0.059 by N log. Okay. Instead of writing minus, we are writing plus. But means product side by reactant side or reactant side by product side? Reactant side by product side. That means concentration of Mn plus. Concentration of Mn plus. So by using this formula, we can calculate reduction potential of an electrode. If you want oxidation potential, simply we have to change the sign. If you have an electrode like this, Zn2 plus copper 2 plus copper, how to get cell potential? E cell is equal to E0 cell minus or plus 0.059 by number of moles of electrons involved 2 log copper plus 2 by Zn2 plus antena Zn2 plus by copper 2 plus Zn2 plus by copper 2 plus. Like this we have to simplify. If the concentrations are same, E0 cell, E cell is nothing but E0 cell. Directly we have to write like this, and anode side ion concentration by cathode side ion concentration. Anode side ion concentration by cathode side ion concentration. If you write plus cathode side ion concentration by anode side ion concentration, and we have to verify whether number of electrons are balanced or not. And okay, if you have like this, for example, Zn2 plus Ag plus Ag, then how to write it? Cell potential E0 cell minus 0.059 by number of moles of electrons involved is 2. Here 2 electrons are involved, here only 1 electron is involved, but here we have to take how many moles of Ag plus? And 2 moles of Ag plus to balance number of electrons. To balance number of electrons, here we have to take 2 moles of Ag plus. So we get log concentration of Zn2 plus by concentration of Ag plus power 2. Concentration of Zn2 plus by concentration of Ag plus power 2. Okay, to balance number of electrons, we have to take 2 moles of Ag plus ions. So we get Ag plus power 2. And okay, next one, at equilibrium, and how to get equilibrium constant? At equilibrium, what about delta G? 0. Delta G 0, that means E is also 0. At equilibrium, delta G or minus NF E cell 0, that means E cell value is 0 at equilibrium. Okay, what is cell potential at equilibrium? Once this question given, and cell potential is 0 at equilibrium. If you apply this condition, okay, and at equilibrium Q value becomes equal to what? K. Q is called reaction quotient, K is called equilibrium constant. What is the formula for equilibrium constant? Okay, in that in the Nernst equation, E we have to substitute 0, and E we have to substitute 0, and in the place of Q we have to substitute K. Then we get equilibrium constant. NF E0 cell by RT, NF E0 cell by RT. So if you write in terms of logarithm, if you simplify 2.303 by 2.303 RT by F, we get 0.059. So N into E0 cell by 0.059. So by using this, we can calculate equilibrium constant. This is the formula for equilibrium constant, N into E0 cell by 0.059. Important and Nernst equation. Okay. For example, we are adding 2 electrode reactions, and electrode reaction 1 plus electrode reaction 2 gives third electrode reaction. Okay, for this E1 not given, E2 not given, E3 not we want to calculate. What is the formula? E3 naught is equal to N1 E1 naught plus N2 E2 naught by N3. Okay, if electrode reaction 1 plus electrode reaction 2 gives third electrode reaction, then third electrode potential we can calculate like this. If subtraction, electrode reaction 1 minus electrode reaction 2 gives electrode reaction 3, then what we get in here? Minus N2 E2 naught. E3 naught is equal to N1 E1 naught minus N2 E2 naught by N3. N1 E1 naught minus N2 E2 naught by N3. Okay, this already we discussed. Delta G we can calculate by using minus NF E cell. How to calculate delta S, and what is the formula? NF into DE cell by DT. NF into DE cell by DT. So from that formula for DE cell by DT, variation of cell potential with temperature, the formula is delta S by NF. The expression for variation of cell potential with temperature is delta S by NF. So if delta S positive, then what happens? Cell potential increases with temperature or decreases with temperature? Increases with temperature. If delta S is negative, cell potential decreases with temperature. If delta S positive, cell potential increases with temperature. If delta S negative, cell potential decreases with temperature. Right, once delta G and delta S are known to us, delta H we can calculate by using this equation. Delta H is equal to what we have? Delta G plus T delta S. Delta G plus T delta S. By using that we can calculate delta H. Okay, this is the calculation of thermodynamic data, equilibrium constant and third electrode potential. Right. Next one, okay, chemical cell without transference. The example for chemical cell without transference is Daniell cell with the salt bridge or without salt bridge? With the salt bridge. Daniell cell with the salt bridge is an example for chemical cell without transference. Okay, and another example we discussed this one, and silver chloride HCl H together, platinum H2 gas 1 atmosphere, silver chloride silver. This is reversed to anions, hydrogen electrode is reversed to cations. HCl is common electrolyte. If you have common electrolyte, even though we are not using salt bridge, that is without transference. So this is also chemical cell without transference. Okay, so we discussed some reactions and okay, already we discussed what is the reaction for hydrogen electrode and silver chloride. Okay, after getting reactions, if you substitute in Nernst equation, we will get cell potential. Okay, right. Next one, chemical cell with the transference. And second example we discussed chemical cell with the transference. Okay, chemical cell without transference ki two examples we discussed. Daniell cell without salt bridge, and this example we have discussed. Chemical cell with the salt bridge and Daniell cell without salt bridge or with porous partition. If you take Daniell cell, if you take with porous partition, if two op cells are separated by porous partition, then in addition to electrode reactions, what happens? Transfer of ions takes place from one op cell to another op cell. So because of diffusion of ions, some excess potential is observed. That excess potential is called as liquid junction potential, or another name is diffusion potential, which is indicated with EJ. So in addition to electrode reactions, because of transfer of ions takes place from one op cell to another op cell, some excess potential is observed called liquid junction potential or diffusion potential, EJ. What is the formula for liquid junction potential? E cathode minus, E with transference minus E without transference. E with transference minus E without transference. How to eliminate liquid junction potential? Liquid junction potential can be eliminated by using salt bridge. Liquid junction potential can be eliminated by using salt bridge. In salt bridge we use strong electrolyte or weak electrolyte? Strong electrolyte. High concentration of strong electrolyte we use. In salt bridge we use strong electrolyte. Next, the conditions are, one is strong electrolyte. What about transport numbers of cation and anion? Transport numbers of cation and anion are same, almost same. Then only liquid junction potential is 0. Transport numbers of cation and anion are same. What are the examples for salt bridges? KCl salt bridge, KNO3, next ammonium nitrate salt bridge. So almost transport numbers of cation and anion are same. That's why specially we use these salt bridges. Another importance of salt bridge is whether transfer of ions occur through salt bridge or no transfer of ions. Transfer of ions occur through salt bridge. Whether transfer of electrons occur or not occur, cannot occur. Transfer of electrons cannot occur through salt bridge, but transfer of ions takes place through salt bridge. Okay, in anodic of cell, it provides sufficient number of cations or anions. Sufficient number of anions. Okay, oxidation reaction takes place. For example, zinc Daniell cell, Zn gives rise to Zn2 plus 2 electrons. Accumulation of positive charge is absurd. Accumulation of Zn2 plus ions is absurd. Okay, so to neutralize the charge, sufficient number of anions are provided. So anions are provided, and at cathodic of cell, sufficient number of cations are provided. So sufficient number of anions are provided in anodic of cell, sufficient number of cations are provided in cathodic of cell. So therefore the importance of salt bridge is it maintains what? Electrical neutrality. It maintains electrical neutrality. If it cannot provide sufficient number of cations or anions, then what happens? Accumulation of charge takes place, electron exchange cannot take place freely, then equilibrium can be attained rapidly, cell reaction will be completed fastly. So by using salt bridge, okay, equilibrium can be attained rapidly or equilibrium cannot be attained rapidly. Equilibrium cannot be attained rapidly. Equilibrium cannot be attained rapidly. These are some advantages we have with the liquid salt bridge. Salt bridge prevents liquid junction potential. Okay, it provides a sufficient number of anions and cations in anodic and cathodic of cell, thereby it maintains electrical neutrality. So free electron flow takes place freely. Because electron flow takes place freely, equilibrium cannot be attained fastly. Okay, and we take salt bridge in the form of gel by using agar-agar, okay, or good pen. By using agar-agar, it can be jellified. It can be jellified, okay, in the form of gel to avoid diffusion effects. To avoid diffusion effects. Agar-agar or gelatin. Agar-agar or gelatin, right? Next one, third one, electrode concentration cell. Electrode concentration cell, we discussed 3 examples. Here same electrode but different concentration. Same electrode but different concentration. Electrode reverse to cation, electrode reverse to anion we discussed. Same electrodes with a different concentration we are passing. Okay. And third example we discussed zinc amalgam, okay, with the C1 concentration which is in contact with Zn2 plus, zinc amalgam with the C2 concentration. These are the 3 examples we discussed. Here electrode reaction is of H2 gas P1 to of H2 gas P2. See, easily you can guess like this, and of H2 gives rise to H plus and at anode. Okay, at cathode what? H plus gives rise to of H2. H plus gets cancelled. So left side what we get, and of H2 at gas P1. Right side what we get? Of H2 at gas P2. Okay, at anode what is the reaction? Of H2 gas P1 gives rise to H plus electron. At cathode reverse reaction. H plus electron gets cancelled. Common electrolyte we are taking. So of H2 at gas P1 is equal to of H2 at gas at P2. When it takes place spontaneously, P1 greater than P2, it takes place spontaneously. Next, if you apply Nernst equation, we have to write like this. E0 cell is 0 for all concentration cells. E0 cell is 0 for all concentration cells and E0 cell is 0 for all concentration cells. No need to concentration on E0 cell. Instead of taking minus, we take plus. RT by NF. How many moles of electrons are involved here? Half H2 gives rise to H plus plus electron 1. Ln. So instead of writing minus, we are writing plus and so what we get? P1 by P2. P1 by P2. How many moles is involved? 1 by 2 moles. So that 1 by 2 we get at the beginning. Okay. For Cl2 we get reverse and for Cl2 we get reverse. Gas P2 to gas P1. Electrode reverse to anion. Here electrode reverse to cation or anion? Cation. So zinc amalgam C1 to zinc amalgam C2 we will get. Easy guess cheyachandi. So zinc amalgam gives rise to Zn2 plus at anode. At cathode what we get? Zn2 plus 2 electrons gives zinc amalgam. So left side we have zinc amalgam at C1 concentration, right side we have zinc amalgam at C2 concentration. So once you know electrode reaction, you can verify all the remaining and we can get cell potential equation if you substitute in Nernst equation. Okay, when it is spontaneous and C1 greater than C2, then this reaction is spontaneous. This is electrode concentration cells. And 2.303 RT by F value is 0.059. While we are solving problems, 2.303 RT by F we have to take as 0.059. Fourth one, electrolyte concentration cell without transference. In this we discussed 4 cases and electrolyte concentration cell without transference we discussed 4 cases. One is electrode reverse to cation. Okay, I am giving one example and platinum H2 gas 1 atmosphere, HCl A1 salt bridge, HCl A2 same H2 gas comma platinum. So same electrolyte with different concentration. So it is an example for electrolyte concentration cell with or without transference. How to verify it? By using salt bridge. We are using salt bridge, so without transference. If electrode reverts to cation, what is the electrode reaction? Cation migrates from A2 concentration to A1 concentration. Cation migrates from A2 concentration to A1 concentration. Okay, if you take copper sulfate, number of moles of electrons involved are 2. Okay, next if you take electrode reverse to anion, what we get? Anion migrates from A1 concentration to A2 concentration. So if A1 greater than A2, the cell reaction is spontaneous. Third case we discussed, end electrodes reverse to cation, end electrodes reverse to anion. That we discussed by combining 2 chemical cells without transference in reverse direction. If you combine 2 chemical cells without transference in reverse direction, if end electrodes reverse to cation, what we get? Electrolyte transfers. Electrolyte transfers from A2 to A1 concentrations. See the difference here also A2 to A1, but only one ion is involved here, both the ions are involved. If end electrodes reverse to anion, what we get? Electrolyte transfers from A1 concentration to A2 concentration. But once you have to practice how to identify a given cell comes under how a given cell comes under electrolyte concentration cell without transfer, that you have to verify once. Okay, for example here if you write E cell E cell we get as RT by NF ln A2 by A1, A2 by A1, or A plus or minus 2 by A plus or minus 1. But here we get, in this case, RT by NF ln same A2 by A1 only, but A plus or minus 2 by A plus or minus 1 whole power 2 we will get. Here both the ions are involved, 1:1 electrolyte. Okay. For 1:1 electrolyte, what is activity? And activity is equal to A plus or minus power 2. So power 2 we will get. E cell is equal to here 2. Here also you write with respect to mean ionic activities. See the difference, and here only one ion is involved, so power 2 we are not getting. Here both the ions are involved, so we are getting power 2. And last one, discussed electrolyte concentration cell with transparency. Electrolyte concentration cell with transparency. Discuss two cases, electrode reverse to cation, electrode reverse to anion. Only the difference is we have to remove this salt bridge, we have to take some porous partition. Okay, electrode reverse to cation, electrode reverse to anion. If electrode reverse to cation, what is the reaction? T minus amount of electrolyte transfers from A2 to A1. A2 to A1 only. If electrode reverse to anion, T plus amount of electrolyte transfers from A1 to A2. Electrode reverse to cation. For example, chlorine gas electrode is in contact with HCl and electrode reverse to cation or anion? Anion. Silver chloride is in contact with Cl minus ions, electrode reverse to anion. Lead sulfate is in contact with sulfate ions, electrode reverse to anion only. Hydrogen electrode in contact with H plus ions, electrode reverse to cation. Copper in contact with copper 2 plus ions, electrode reverse to cation. So those 5 examples we discussed. Okay. Next one, liquid junction potential. And liquid junction potential means Ej is equal to E with transference minus E without transference. Okay. So here we get E with transference, here we get E without transference. If you subtract, we will get liquid junction potential expression. So what is the expression? Same expression we have whether electrode reverse to cation or electrode reverse to anion, that is T minus minus T plus into RT by NF ln A plus or minus 2 by A plus or minus 1. This is the common reaction we have whether electrode reverse to cation or electrode reverse to anion. Same expression we have for liquid junction potential. So liquid junction potential is directly proportional to difference in the transport numbers of cation and anion. So if transport numbers of cation and anion are same, that is 0.5, then what about liquid junction potential? 0. So liquid junction potential cannot be erased. The speeds of cation and anion are same. The speeds of cation and anion are same, then liquid junction potential cannot be erased. Okay. For example, we are taking an electrolyte MCl where M may be H plus or sodium plus or lithium plus or K plus. When liquid junction potential is high, and if M is equal to H plus, then liquid junction potential is high. Okay, in each case transport number of chloride ion T minus is same, but where we get T plus value high and H plus, transport number of H plus is high, so where the difference, maximum difference we will get. And if you take in the place of M H plus, we will get maximum difference, so therefore liquid junction potential is high if M is equal to H plus. Next we discussed determination of transport numbers also. If electrode reverses to cation, we get transport number of anion, that is E with transference by V without transference. If electrode reverses to anion, we get T plus. Here if electrode reverses to cation, we get transport number of T minus. If electrode reverses to cation, anion, we will get T plus. And same ratio if you do, we get T plus. So same, and the equations are same. There also we have electrolyte transfers from A2 to A1. What is the extra we are getting? And T minus extra we are getting. That's why if you do E with transference by E without transference, we will get these transport numbers. Okay. Next we discussed potentiometric titrations. Conductometric titrations also we discussed briefly. We discussed conductometric titrations. If you take strong acid versus strong base, how we will get it? Nature of graph, conductance versus volume of NaOH. Sharp decrease and sharp increase. Here H plus ions are replaced by Na plus ions, and here Na plus comma OH minus ions increases. After end point, no reaction, so Na plus and OH minus ions increases, so therefore conductance increases. Acetic acid versus NaOH, what we get? Slow increase and sharp increase. Slow increase is due to acetic acid. In the place of acetic acid, what we get? Sodium acetate salt we will get. Acetic acid is replaced by sodium acetate, and after end point Na plus and OH minus ions increases, so sharp increase. Third one, mixture of acids, HCl and acetic acid versus NaOH. What we get? First, which one participates in the reaction? HCl, so sharp decrease, and acetic acid slow increase, and after that Na plus and OH minus. So V1 is the volume of NaOH required to neutralize what? HCl. Okay, this is okay, V1 I am taking. This is the volume of NaOH required to neutralize HCl. If you take this one as V2, okay, what about volume of NaOH required to neutralize acetic acid? V2 minus V1, that is the volume of NaOH required to neutralize acetic acid. Here you write acetic acid. Volume of NaOH required to neutralize acetic acid is V2 minus V1. As long as HCl present, whether acetic acid involved in the reaction or do not involve in the reaction. Not involved in the reaction, that is due to common ion effect. That is due to common ion effect. And because of common ion effect, acetic acid do not involve in the reaction as long as HCl present. So as long as HCl present, its dissociation cannot occur. Fourth one we discussed weak acid, strong acid versus weak base. Strong acid versus weak base. HCl versus ammonium hydroxide. Okay, H plus ions are replaced by ammonium ions, so sharp decrease. Ammonium hydroxide is a weak electrolyte, so no change. Okay, as ammonium hydroxide is a weak electrolyte, after end point no change in the conductance. And tarvata acetic acid versus ammonium hydroxide. Weak acid versus weak base. Initially slow increase, that is due to formation of what? Ammonium acetate. Acetic acid is replaced by ammonium acetate. So the number of ions increases, so conductance increases. After that, is there any change or no change? No change. As ammonium hydroxide is a weak electrolyte, almost conductance remains the same. Initially slow increase, after end point no change. Next, mixture of acids if you take. So combination of these two. That is HCl sharp decrease, after that acetic acid slow increase, after that ammonium hydroxide no change. H plus ions are replaced by ammonium ions, so sharp decrease, number of ions increase, slow increase, and ammonium hydroxide, so no change. Next we discuss the salt of weak acid with strong base versus strong acid. Antena? Salt of weak acid with strong base versus strong acid. Then what happens? CH3COO Na plus HCl. CH3COOH plus NaCl is formed. That means CH3COO minus ions are replaced by Cl minus ions. Okay. In the place of sodium acetate, we will get NaCl. Okay. NaCl. That means sodium ions are same. Acetate ions are replaced by chloride ions. Okay. Whenever acetate ions are replaced by chloride ions, conductance decreases. After that HCl we have sharp increase is observed. Okay. Here CH3COO minus ions are replaced by what? Cl minus ions. CH3COO minus ions are replaced by Cl minus ions. That's why it's decrease. After that H plus and Cl minus ions are increased, so sharp increase. Salt of weak acid with strong base versus strong acid. Salt of weak acid with strong base. CH3COO Na is the salt of acetic acid versus NaOH. Okay. And lastly we discuss salt of weak base with strong acid, that is NH4OH plus HCl. What we get? NH4Cl versus strong base. Salt of weak base. Okay, salt of weak base with strong acid versus strong base. So what we get? NaCl plus ammonium hydroxide. NaCl we are getting, that means ammonium ions are replaced by sodium ions. But the conductivity of ammonium is more compared to sodium. Increase kada? Conductivity of Cl minus ions are more. So slow increase. After that, that is the end point. Here CH3COO minus ions are replaced by Cl minus ions. So the conductivity of Cl minus ions more compared to acetate ions. Okay. Here NH4 plus ions are replaced by sodium ions. The conductivity of NH4 plus is more. So therefore decreases. Conductivity decreases. After that increases. Increase is due to Na plus gamma OH minus ions. Decrease is due to NH4 plus ions are replaced by sodium ions. NH4 plus ions are replaced by sodium ions. Lastly, precipitation titration also we discussed. Precipitation titration. Silver nitrate versus KCl. So AgNO3 is replaced by what? KNO3. During reaction what we get? And KNO3 we will get. That means Ag plus ions are replaced by K plus ions. Ag plus ions are replaced by K plus ions. So, but conductivity values of Ag plus and K plus are almost same. conductivity values of Ag plus and K plus are almost the same, so no change. After that K plus and Cl minus ions increases, so conductivity increases. So like this we can get end points. And so these are from conductometric titrations. And so afternoon we discussed potentiometric titrations, and electrolysis we have to discuss. Okay, electrolysis, Faraday's laws, Kohlrausch law applications, అంతే అవి డిస్కస్ చేస్తే సరిపోతుంది. డీబైహాకల్ థియరీ అవన్నీ కింద కొన్ని పాయింట్స్ గుర్తుపెట్టుకునేది ఉంటాయి. డీబైహాకల్ థియరీ నుంచి డీబైహాకల్ లిమిటింగ్ లా, నెక్స్ట్ ఈ ఎలక్ట్రోడ్ పోలరైజేషన్ వీటి నుంచి అయితే అసలు ప్రీవియస్లీ క్వశ్చన్స్ నాట్ గివెన్ అండి. ఓకే, ఎలక్ట్రోడ్ పోలరైజేషన్, ఓవర్ పొటెన్షియల్, నో క్వశ్చన్స్ ఆర్ నాట్ గివెన్. ప్రీవియస్ సో ఫార్ క్వశ్చన్స్ నాట్ గివెన్ ఫ్రమ్ those concepts, but you may remember that how to prevent electrode polarization or how to prevent over potential by using depolarizers, by continuous agitation, or by increasing temperature, or by using rough electrodes. That we may expect and from that concept. Okay, so afternoon we will discuss potentiometric titrations and electrolysis and Kohlrausch law. Okay, so afternoon timings 3:30కి స్టార్ట్ చేయమంటారా? 3గా తొందరగా స్టార్ట్ చేసుకుంటే బెస్ట్ ఏమో. 3 to 4:30 ఫిజికల్ అండి. సో ఆఫ్టర్ దట్ ఆర్గానిక్, అండ్ ఇఫ్ పాసిబుల్ అగైన్ ఐ విల్ కంటిన్యూ. ఓకే రైట్, 3 to 4:30 physical, I will complete this electrochemistry, and after that you have 1 hour organic class, and after that if possible I will continue that magnetic properties from solid state. Okay, right, thank you. So solid state quick revision we will discuss next week, and okay, right. Yes, solid state quick revision, atomic structure and quantum chemistry also, those we will discuss in the next week. So once you revise those also, atomic structure, solid state and quantum chemistry.